Hi everyone, welcome to One Stop Mathematical Solution. Today we are going to see CSIR NET June 2012 question paper. In this video we only deal about complex analysis part. First question, question 33. Let f from C to C be a complex valued function of the form f of z is equal to u of xy plus iv of xy. Suppose that u of xy is equal to 3x square y, then. So, we have given a complex valued function and u is defined. Then we have to check which of the following option is true. So, in the option they are asking about the holomorphic conditions and differentiability of u. So, first of all, we'll look into the concept. So, if f of z is equal to u of xy plus iv of xy, then f is holomorphic if and only if u and v are harmonic. So, we'll check what is harmonic now. So, u is harmonic if uxx plus uyy equal to 0. Uxx means second derivative of u with respect to x, and uyy means second derivative of u with respect to y. We have to find that and take its sum, and if it is equal to 0, then u is harmonic. So now let's go to the question. So we have given u is equal to 3x square y. So to check f is holomorphic, we have to check whether u is harmonic. That is, we have to take its second derivatives. So first of all, I am taking ux, that is equal to 6y we get. Again we will differentiate, we get uxx is equal to 6y. Similarly, we will take uy, that is equal to 3x square, and we will get the second derivative as uyy equal to 0. Now we are taking these two sum, so we will get uxx plus uyy equal to 6y. So for y equal to 0 only, this equation is becoming 0. For all other term, it is not becoming 0. That is, this is not equal to 0 for every y not equal to 0. So this implies u cannot be harmonic. Therefore, our function f is not holomorphic. So let us now check the correct option. So we have got f as not holomorphic, and u is clearly is differentiable with respect to x and y. So option D cannot happen, and we got f is not holomorphic. So A, B, C, D doesn't happen. So our correct option is A. Next question, question 37. The power series sigma n is equal to 0 to infinity 3 power minus n z minus 1 whole power 2n converges f. So we have to check where this power series converges. So we will first look into the concepts. So if we are given a power series sigma n is equal to 0 to infinity an z minus z0 whole power n, then its radius of convergence is given by this formula. We have here two formulas. We can use any of these according to the power series. So that is 1 by r is equal to limit n tends to infinity modulus an whole power 1 by n, or this is equal to limit n tends to infinity modulus an plus 1 divided by an. So an here is the coefficient of this power series. Also we know that this power series converges in this circle of convergence, that is modulus z minus z0 less than r, and diverges for mod z minus z0 greater than r. So we'll go into the question. So we have given the power series sigma n is equal to 3 minus n z minus whole power 2n. First of all, we are finding its radius of convergence by using the first formula. So 1 by r is equal to limit n tends to infinity modulus 3 power minus n whole power 1 by n. So when we simplify this, we'll get limit n tends to infinity 3 power minus n. Here it doesn't contain any n term. So this is a constant. So this is equal to 1 by 3. So we'll get 1 by r is equal to 1 by 3. Therefore, r is equal to 3. So the power series converges for mod z minus z0. Here z0 is 1 and modulus whole square, because if we rearrange it in the general form of power series, we'll get this form. So this is equal to mod z minus 1 whole square less than 3. That is mod z minus 1 less than root 3. So this is the region where the power series converges. So now let us look into the correct option. So we have got mod z minus 1 less than 3. So our correct option is option C. So next question 80. Let f from C to C be a neuromorphic function analytic at 0, satisfying f of 1 by n is equal to n by 2n plus 1 for n greater than or equal to 1, then. So we are given a neuromorphic function which is analytic at a point 0, which is satisfying this equation. Then we have to check which of the following equation is correct. So we have to look, this is a part C question, so we have more than one equation correct. First of all, we'll look into the concept. So in the question, we have seen f is a neuromorphic function. First of all, we'll look what is a neuromorphic function. So neuromorphic function is a function that is analytic on all of its domain except for finite number of poles. So the neuromorphic function means that function has only poles as singularities and the poles are finite. And we have to look, poles are obtained by equating the denominator to 0. So we look into the question now. So we are given f of 1 by n is equal to n by 2n plus 1. Here I am replacing 1 by n by z so that it is easy to find the values. So f of z is equal to 1 by z by 2 by z plus 1. So after the simplification we are getting this is equal to 1 by 2 plus z. So now we'll check each options separately. So come on. So already we have seen first option is asking the value of f of 0. So instead of z, replace it as 0. So we'll get f of 0 is equal to 1 by 2 plus 0. So therefore we are getting f of 0 is equal to 1 by 2. Similarly, okay, next option is asking for the poles of f of z. So we'll check its denominator. So it is 0. So 2 plus z equal to 0. This implies z is equal to minus 2. Therefore, f has a single pole at z equal to minus 2. And the third option is asking about the value of f at 2. So substitute 2 in this. So you'll get 1 by 4. And last option is asking about no such neuromorphic function exists. But we have got f of z is equal to 1 by 2 plus z. So it is having only poles or singularities and it is finite. So f is a neuromorphic function. So option D is not true. So we have got f of 0 as 1 by 2, f as simple pole at z is equal to minus 2 and f of 2 is equal to 1 by 4. The correct options are A, B and C. Next question 81. Let f be an entire function. If imaginary f is greater than or equal to 0, then. So we are given an entire function and its imaginary part is greater than or equal to 0. Then we have to check which of the following is correct. So we'll first of all look into the concept. So in the question we have given f as an entire function. I guess all of you know what is entire function. Entire function means the function is analytic everywhere. I have not written this in this concept, but I have to note that. Now we'll see what is Liouville's theorem. So it states that any entire bounded function is constant. So entire bounded is constant function. And now we'll see what is a bounded function in complex analysis. So f of z is bounded if there exists an positive m, that is m greater than 0, such that modulus f of z is less than or equal to m for every z. And third is a property of exponential. You know that, it's simple. Modulus e power z1 plus z2 is equal to modulus e power z1 into modulus e power z2. And for this also a property, that is modulus e power iw is equal to 1 always. So now let us look into the question. So we have given f as an entire function. So let me take f as u plus iv, and it is given imaginary of f is greater than 0. So imaginary part here it is v. So I am writing v greater than 0. So now I am taking e on both sides, that is e power v is greater than or equal to e power 0. You know e power 0 is equal to 1. So this implies e power v is greater than or equal to 1. So from this we will get, I am taking the inverse so that the equation becomes e power minus v less than or equal to 1. Now we will proceed with this. So now I am defining another function z. So let g of z is equal to e power I f of z. You know exponential is always entire. So g of z is entire. Now I am checking whether g is bounded. So you have to take its modulus value. So modulus g of z is equal to modulus e power I f of z. Now I am substituting f of z. So this is equal to e power I into u plus iv. So when we simplify, we will get this is equal to modulus e power iu minus v. Now I am splitting this modulus. So this is equal to modulus e power iu into modulus e power minus v. We know that this is always 1. So this is equal to modulus e power minus v. We know that exponential is always greater than 0. So we will remove this modulus inequality. So we will get e power minus v. We already got that e power minus v is less than or equal to 1. So I am substituting that. So we will get e power minus v less than or equal to 1. So mod g of z is less than or equal to 1. Therefore, g is bounded by its definition. So we have got an entire and bounded function. Therefore, when we use Lively's theorem, we get g of z as a constant. So now we have got g of z as constant. We have taken g of z is equal to e power I f of z. Therefore, e power I f of z equal to c. I am taking some c as a constant. So when I apply log on both sides, I will get I f of z is equal to log c. Therefore, f of z is equal to minus I log c. So this is a constant value. Therefore, f of z is constant. When f is constant, its first derivative and all its higher derivatives equal to 0. That is written here. F is constant doesn't imply f should be 0. It can be any constant. And f is constant means its real part and imaginary part both are constant. So now we'll check what are the correct options. So we got f is constant and real part of f is constant. So our correct options are A and B. So next question, let f from d to d be a holomorphic with f of 0 is equal to 0 and f of 1 by 2 is equal to 0, where d is equal to z of all z such that mod z less than 1. Which of the following are correct? So when f is holomorphic with these two conditions being satisfied, we have to check which of the options is correct. So let us look into the concept first. So whenever we are given such type of question, we always use Schwarzschild lemma or lemma related to this. So mod f of f dash of z is less than or equal to 1 minus mod f of z square divided by 1 minus z square. Do remember this. This might be useful for your exams. So now we'll look into the question. So we have given f of 0 is equal to 0 and f of 1 by 2 is equal to 0. So we have an option that f of z is equal to z for every z element of D. But that is not true, because if f of z is equal to z, then we have to get f of 1 by 2's value as 1 by 2. But it is given f of 1 by 2 is equal to 0. Therefore, we have f of z not equal to z for every z element of D. Next, we need modulus f dash of 1 by 2's range. So that there we are using this lemma. So we'll get modulus f dash of 1 by 2 less than or equal to 1 minus mod f of 1 by 2 whole square divided by 1 minus 1 by 2 whole square. Now we'll substitute f of 1 by 2's value. So we'll get 1 minus 0 divided by 1 minus 1 by 4. Simplify this, you'll get equal to 4 by 3. Therefore, f dash of 1 by 2 is less than or equal to 4 by 3. Similarly, we'll find modulus f dash of 0 is less than or equal to 1 minus f of 0 whole square divided by 1 minus 0 square. Substitute and simplify, we'll get the value as 1. So f dash of 0 is less than or equal to 1. So now we'll check which of the options are correct. So we have got option A as correct and option B as correct. Also these two values are correct, so option C also will come. So these are the correct options. So next question 83. For z element of C of the form z is equal to x plus iy, define h plus is equal to set for z in C such that y greater than 0, h minus is equal to set for z in C such that y less than 0, L plus is equal to set for z in C such that x greater than 0, L minus is equal to set for z in C such that x less than 0. The function f of z is equal to 2z plus 1 divided by f is 5z plus 3 maps. So we have to find what this function maps. So we are given 4 options. All options are asking where this h plus is mapped to and h minus is mapped to. So we are looking into the question now. So we are given f of z is equal to 2z plus 1 divided by 5z plus 3. I am denoting f of z as w. Therefore, we get w is equal to 2z plus 1 divided by 5z plus 3. Now I am simplifying this so that I'll get z in terms of w. So come on, let's do that. So I am cross multiplying this, so we get w into 5z plus 3 equal to 2z plus 1. Now I am taking z terms in one side and constant and w terms in other side. So we get z into 5w minus 2 equal to 1 minus 3w. From this we get z in terms of y, that is z is equal to 1 minus 3w divided by 5w minus 2. Now I am substituting z is equal to x plus iy and w is equal to u plus iv. So we will get x plus iy is equal to 1 minus 3u minus 3iv divided by 5u minus 2 plus 5iv. Now I am multiplying numerator and denominator by the conjugate of the denominator. So we'll get like this. Now I'll multiply and simplify so that I'll write real part separately and imaginary part separately. So we'll get x plus iy is equal to 1 minus 3u into 5u minus 2 minus 15v square minus iv into 5 into 1 minus 3u plus 3 into 5u minus 2 divided by 5u minus 2 whole square plus 25v square. Now I am equating real parts and imaginary parts. So you get x is equal to 1 minus 3u, 5u minus 2 minus 15v square divided by 5u minus 2 whole square plus 25v square, and y is equal to minus v of 5 into 1 minus 3u plus 3 into 5u minus 2 divided by 5u minus 2 whole square plus 25v square. So when we do this simplification, we are getting y is equal to v divided by 5u minus 2 whole square plus 25v square. So in the question we have seen that options they are asking where this h plus and h minus is mapped to in every options. So we are concerned about only the y part. So we are not checking for x. Now we are only looking for y. So when we look, y is dependent on the sign of v and v is dependent on the sign of y, because denominator is always positive because all the terms are squares. So the sign of y depends on sign of v and vice versa. So y greater than 0 means v should be greater than 0, and y less than 0 means v less than 0. So v naught y less than 0 denote h plus, v greater than 0 denotes h plus. So both h plus is mapped to h plus, and secondly h minus is mapped to h minus. Now we'll go to the options. So our correct option is A. Next question 84. At z is equal to 0, the function f of z equal to exponential of z by 1 minus cos z has. So we have to check whether f of z has removable singularity, pole, or essential singularity at z equal to 0. First of all, we'll check the concepts. So this is the Lorentz series expansion of f of z. So that is f of z is equal to sigma n is equal to 0 to infinity an z minus z0 whole power n plus sigma n is equal to minus 1 to minus infinity dn z minus z0. So this term of the expansion is called Taylor part, and this is called the principal part. So f of z has removable singularity if it doesn't have principal part. So f of z has removable singularity if it only contains the Taylor part, and it has pole if it has finite terms in principal part, and if it has infinite terms in principal part, then it has essential singularity. Also note, limit z tends to z0, f of z exists finitely, then z0 is removable singularity. Limit z tends to z0, f of z exists finitely and it's non-zero, then z0 is a pole. Limit z tends to z0, f of z doesn't exist, then z0 is essential singularity. So now we'll go to the question. So we are given f of z is equal to z by 1 minus cos z. We have to check at the point z is equal to 0. So we are finding limit z tends to 0 f of z. So now I am substituting f of z, that is limit z tends to z 0 exponential of z by 1 minus cos z. If we directly apply the limits, we are getting exponential of 0 by 0. So it is the indeterminate form. So we are applying an hospital rule in this term. So we'll get equal to limit z tends to 0 exponential of 1 by sin z. Now we'll apply the limits. So we are getting exponential of 1 by 0, that is equal to exponential of infinity. You know this term doesn't exist. So we have got limit z tends to 0, f of z doesn't exist. Therefore, our point 0 is an essential singularity. Now we'll check the correct options. So we have got z is equal to 0 as an essential singularity. So our option C is correct. We know if f of z has essential singularity around 0, then it has infinitely many terms of principal part. So it has infinitely many negative powers of Z. Doesn't talk about positive powers, so we can neglect the option D. So our correct option is C.